Hello AP Chem students and welcome to topic 8.10, buffer capacity. The learning objective for today is 8.10.a, explain the relationship between the buffer capacity of a solution and the relative concentrations of the conjugate acid and conjugate base components of the solution. Now, as a reminder, you're not going to have to do any calculations with how the pH of a buffer solution changes if you add acid or a base. So this is purely a qualitative discussion. So we would expect to be able to handle more acid or handle more base, or the buffer would shift to make more conjugate base or more weak acid and so on and so forth. So keep in mind that the buffering capacity of a buffer solution is the amount of H plus or OH minus ions that a buffer can absorb, that should say can, without significant pH change. So remember that the two factors that impact the pH of a buffer are the ratio of conjugate base to weak acid and the pKa. Remember, you can also have a buffer that is conjugate acid and weak base. So we think about the pKa. A buffer is most effective if it falls to 1 pH on either side of the pKa. So you can see that here. So 82% is plus or minus 1. And then after that, the capacity of the buffer sharply falls off. So you want to stay within 1 pH unit of the pKa of the weak acid. So if you increase the concentration of the buffer components while maintaining that ratio of being close to 1, you can increase the capacity of the buffer to neutralize added acid and base. And here's a really nice graph that I found illustrating that. So if this is acid added to pure water, so pure water starts at 7, if you add HCl, then you can see that this goes straight down. Now, if we use a buffer, you can see two different buffers here. So we have the red dots, which is the 0.1 molar buffer, and then we have the yellow dots, which is the 0.2 molar buffer. So you can see we can add HCl, add HCl, add HCl, add HCl, and then the 0.1 molar buffer sharply drops off here at 10 to the negative 2, whereas the 0.2 molar buffer continues to stabilize to 10 to the negative 1. And then if we kept going, we would expect that to drop off at some point as well. But strictly by doubling the concentration, and this is still not a very concentrated buffer, right? 0.2 molar. But that change has made a huge impact in the buffering capacity. So maybe my computer will let us keep going. Here we go. So realize that as an acid or a base is added to a buffer, the proportions, that ratio of the conjugate acid-base pair will adjust. So over time, the buffering capacity will change. If the buffer has more conjugate acid than base, it has a greater buffering capacity for added base, right? Because if this is the situation here, no, sorry, this is flipped. If this is the situation here and you have a greater concentration of conjugate acid, then it can accept more base because it has an excess of conjugate acid to react with the base. Now, if the buffer has more conjugate base than acid, which is what we see here, then it has a greater capacity for acid, right? And you can just kind of reason through that, okay? So thinking about the bar graphs that we looked at in previous videos, it's a little bit like a seesaw, okay? And this is really a sort of an application of Le Chatelier's principle as well. Okay, so what should you be able to do with this? Qualitatively describe if a described buffer will be able to accommodate additional acid or base. That's it, because we've really hit on buffer capacity in previous videos without actually like drilling down and just focusing on it, but it should make sense now. So that is it. I will see you soon to talk about pH and solubility.